This video is on Hamiltonian graphs. A Hamiltonian cycle in a graph is a cycle that includes each of the vertices of the graph. Recall that a cycle cannot repeat vertices, so this means that in a Hamiltonian cycle, each of the vertices is contained exactly once. So a graph is Hamiltonian if it contains a Hamiltonian cycle. And so our question is, which graphs are Hamiltonian? Note that this is similar to the question from the last lecture. So last lecture we talked about Eulerian graphs and said which graphs are Eulerian. That is, which graphs have a circuit through the graph that contains each edge exactly once. So previously, is there some circuit that contains each edge exactly once? Now, is there some cycle that contains each vertex exactly once? So let's start by considering some examples and try to figure out which of the following graphs and multigraphs are Hamiltonian. As you're thinking about these, can you make any conjectures about when a graph will or will not be Hamiltonian? So let's look at an example. Let's look at, for example, M1. So is there some cycle through M1 that contains each vertex exactly once? And yes, there is. So we could start, say, at this vertex and go through a cycle that contains each vertex exactly once. Note we do not need to include all of the edges. So we just need each vertex to be passed through exactly once, and if that is possible, then yes, that graph is Hamiltonian. So take a moment to try these out. Try to figure out which ones you think are Hamiltonian, which ones you think are not, and we will talk about them below. Okay, let's take a look at these. So which of these graphs and multigraphs are Hamiltonian? That is, contain a cycle that contains each vertex exactly once. And can you make any conjectures about when a graph will or will not be Hamiltonian? So we already looked at M1 and saw that it was Hamiltonian. Let's now look at K4. Say that we start at this vertex and use this edge, then this edge, then this edge, then this edge. And yes, that's a cycle that contains each vertex exactly once. So K4 is a yes. W, let's try that out. Let's say that we start at this vertex and go on this edge, this edge, this edge, this edge. And now we have two ways we could go. We could either go up, and notice that if we go up, we would get stuck. So if we go up, we get stuck because at this point, we cannot repeat this vertex. This vertex has already been visited, so we're stuck. Whereas if we had gone this way, we would again get stuck at this point and we would never visit this vertex. So this vertex would be left unvisited. So right now we think the answer is no. We have not found a Hamiltonian cycle for that graph, but we haven't exactly proved that there isn't one. Let's look at M3. Well, it looks like there's a pretty standard cycle for that as well. So 1, 2, 3, 4, and it doesn't matter which edge we pick, but we have started and stopped at the same vertex. We had included each of the vertices on that cycle, and we haven't included all of the edges, but that's okay. So we found a Hamiltonian cycle, therefore M3 is Hamiltonian. Let's look at P. This is the Peterson graph. So it could start anywhere. Let's start here, and I guess it would be most natural to go around. And then at this point we could go up. If we go up, we're stuck because we would have visited this vertex and we couldn't get out of it. If we go over, we could visit some vertices here, and then at some point we would be stuck again, so we couldn't leave that vertex, and we would not have returned to our starting point. So we think that this is probably a no, but we haven't shown that there is no Hamiltonian cycle. We've just shown so far that the particular cycle we tried didn't work. let's see, with G, there's a pretty obvious Hamiltonian cycle there, a cycle that includes every vertex exactly once. So yes, G is Hamiltonian. How about H? Well, if we start here, we could start to include the vertices in some kind of cycle. And notice we are stuck at this point, so we could go around, but now we've revisited this vertex without having gotten back to where we started. So again, we haven't proved it, but we don't see one right away. And with M2, let's say that we start here and we go in a cycle around, and we're doing okay so far. But now we have already visited this vertex and we want to visit it again. A Hamiltonian cycle can only contain each vertex exactly once, so we think the answer is no here as well. Okay, so check that out with the answers that you had. Notice that we say yes, period, for those graphs that do have a Hamiltonian cycle. If we found a cycle that contains every vertex, then by definition that graph is Hamiltonian, whereas all of our no's are followed by question marks, because to prove that a graph is not Hamiltonian, you have to show that no such cycle can exist on that graph. It could theoretically be the case that you started to try to draw a cycle, and the way that you started to try to draw it, you got stuck, but if you'd started in some other way, it might have worked. So there's sort of more to show when you're trying to show that a graph is not Hamiltonian. So I also asked you to think about any conjectures about which graphs would be Hamiltonian and which ones would not. And there certainly are certain classes of graphs that you can say are Hamiltonian and other classes of graphs that you can say are not Hamiltonian. However, there is no one characterization of Hamiltonian graphs. That is, given a general graph, there is no one simple test to determine whether or not that graph is Hamiltonian. And in fact, this is a very famous problem that's in the class of NP-hard problems. Also happens to be NP-complete. We'll describe this more in the next video, but for now, just as a simplification, if you have a graph on n vertices, there is no known polynomial time algorithm to determine whether or not that graph is Hamiltonian. So there's no algorithm that takes a polynomial in terms of the number of vertices, a polynomial amount of time in terms of the number of vertices. So this is in a set of very famous problems that we'll discuss in the next video. Essentially what this means is that this is a really difficult problem. So it's really difficult to determine whether a graph has a cycle that contains every vertex exactly once. And this is in strong contrast with determining whether a graph is Eulerian. Remember that G is Eulerian, has a circuit that contains each edge exactly once, if and only if every vertex has even degree. So this is a super simple test to determine whether or not a graph has an Eulerian circuit, whereas there is no good test, no single good test to determine whether or not a graph is Hamiltonian. So even though there is no general categorization of which graphs are Hamiltonian, for some graphs there are criteria that we can apply to show that a graph is not Hamiltonian. Let's consider the graphs from above that we think are not Hamiltonian. So these are just copied and pasted from above. Let's start by thinking about the graph M2. So if we started, say, here, and we go around somehow, okay, we have visited this vertex, we visited this vertex, and now we could go in either direction. Let's say that we visit this vertex next, and then this vertex, and then go back. To get back to where we started, to complete the cycle, we would need to visit this vertex again. We would need to repeat this vertex. But by definition, a cycle does not repeat vertices. And we can argue that for this graph, there is no way to start and end at the same vertex and include all vertices without repeating this vertex in the middle. Because if we start on this side, we have to pass through it to get over to the right side, and then we'd have to pass through it again to get back to where we started. Same argument for if we started on the right side. And if we'd started in the middle, then we would end up repeating the vertex more than once as well. So that vertex that we need to repeat, let's call that the vertex V. V is a cut vertex. What that means is that V sort of cuts the graph in half. Removing the vertex V puts the graph into two different pieces. And because the graph has a cut vertex, that means the graph M2, or really the multigraph M2, is not Hamiltonian. Anytime that we have a cut vertex, it will be the case that we cannot get from one side of the graph to the other without repeating that, to the other and back without repeating that cut vertex. Okay, do we see that anywhere else? Well, we also see it here with the graph H. We could call that U. That vertex U is also a cut vertex. And so again, this graph H is not Hamiltonian for the same reason. So this graph H is not Hamiltonian because if we, say, start here, then we'd have to pass through U once to get to the other side, and we'd have to pass through U again to get back to the beginning. So U would be repeated if we tried to do some kind of cycle. Similarly, if we started here, same deal, we'd have to go through U on the way to the left side and go through U again on the way back. Or if we began with U, then we would go through these other vertices and go around again and repeat U before coming back to it. So U is a cut vertex. If we try to make a cycle, we must repeat the vertex U, a cycle that includes every vertex, and so H is also not Hamiltonian. Okay, the other two graphs don't appear to have a cut vertex, a vertex that, if we removed it, would break the graph into two pieces. But is there something kind of similar going on over here with W? Let's see. So if I try to, say, start here, I could go through, and again, I have sort of two choices. And I could either go up, and in that case I would get stuck, and this vertex would need to be repeated, or I could go over, in which case I would have missed this vertex. So this is sort of an argument that this is not a Hamiltonian graph. In fact, there's something a little more general than a cut vertex here. What we have is a cut set. So if this is the vertex U and this is the vertex V, then the vertices U and V form a cut set. So what we mean by that is if we consider the graph W minus the vertices U and V, so if we remove those two vertices, then we know that an edge can't exist unless it has two vertices incident with it. So the graph W minus the vertices U and V would just be that we have these two vertices on the side. We have this vertex in the middle, and we would have these other two vertices on the side. So both U and V were removed, and so were all the edges incident with U and V. And so, therefore, what do we have left? We have a graph left with three components. And so we have three components remaining, in other words, three connected pieces in the graph W minus UV. And so essentially the same issue happens as when we have a cut vertex. When we have a cut vertex, that means over here that H minus the vertex U has two components. has two pieces that are each connected but not connected to each other. And similarly over here, M2 minus the vertex V has two components. And so to get from one component to the other, we have to go through V more than once. Similarly, over here, we now have three components. And so to get from one piece of this graph to another one of the two pieces, we have to go through either the vertex U or the vertex V each time. And so each time we leave and come back from one of these components, we must go through one of these two vertices in the cut set. And this means that there is no Hamilton cycle for this reason, because we must go through and come out of these vertices too many times in order to start in one place and end back up at the beginning. So for a more formal statement of what we just discussed, here's this theorem. If G contains a set of vertices S such that the number of components in G minus S is greater than the size of S, then G is not Hamiltonian. So for the graph H above, the set S was just the single vertex U, and the number of components in H minus S was 2, which is greater than the size of S, which is 1. In the graph M2 above, the set of vertices is again just that single vertex V, and so the number of components in M2 minus S was 2. There were 2 components remaining, which is greater than the size of S, which was 1. And in the last example, in the graph W, we saw that the set S was the set of 2 vertices U and V, those 2 vertices in the cut set, and the number of components in W minus S, the number of components in W when you take away those 2 vertices was 3. There were 3 components, which is greater than the size of S, which is 2. So each of those graphs above met this criteria, some set of vertices S, such that the number of components in G minus S is greater than the size of S, and this tells us that G is not Hamiltonian. Again, as an informal proof, the reason for this is that if we need to make a cycle that starts and ends at the same vertex and contains all vertices, this cannot be done when such a set S exists, because anytime we go from one component to another, we must move through one of the vertices in S, and the number of components that we move through is larger than the number of vertices that we can move through. So one of those vertices in S would need to be repeated if we tried to include every vertex. Okay, so we found one criteria to show that a graph is not Hamiltonian. However, this graph, the Peterson graph, is also not Hamiltonian. However, there is no set S as described above. There is no set of S of vertices of the graph P, such that if you took away those vertices, there would be more components, more pieces than there were vertices in S. So this is telling us that this theorem does go in one direction, but it is not an if and only if theorem. So in other words, even if you can't find such a set of vertices S, that does not tell us that the graph is Hamiltonian. So this is not an if and only if theorem, and of course we know that it isn't, because as I said above, there is no simple criteria or no single criteria to determine whether or not a graph will be Hamiltonian. If this theorem was if and only if, then that would be such a criteria. In the next video, we'll both give some more examples of graphs that are and are not Hamiltonian. We'll use this criteria some more, and we will also discuss the class of problems that are NP hard and the class of problems that are NP complete.